So this is the Unit 6 quiz. All right, so for Part A is some of the Unit 5 stuff that's included on the quiz. So this is when we did the absolute values. So it says, for given f of x is equal to the absolute value of x, how are each of the graphs changed compared to f of x? So if we look at g of x, the thing that's different compared to the absolute value of x is we have the 1/7 out front. So remember, if there's a number out front, it's either going to be a stretch or a compress. So in this case, you could say either it's stretched by 1/7 vertically, because we're kind of stretching by 1/7, which actually shrinks it. Or you can say that it's a vertical compression. So you could say it's compressed as well. Either one will be okay. If we want to check it out, we can double check it with the graph. So we can type in absolute value of x. And then just to show on the on-screen keyboard, if we want to do the other one, that's 1/7. And then the absolute value bars are just right here. So we'll do absolute value of x. So we can see that, yeah, it gets shrunk down. It gets compressed. Now, again, since I said a vertical stretch by 1/7, I'm like stretching by a fraction. So that means it's shrinking. But that's just more of a technical thing. So for part B, we have x plus 3. So we see we have the number inside the absolute value. So that means that we're either going to go to the left or to the right. So we're going to choose one of those. And inside is the opposite. So it looks like we should be going to the right. So we're actually going to go left. So we're going to shift left 3. And again, we can double check that. Let's go back to our graph. So if we change this, get rid of the 1/7 and instead do x plus 3, we can see that, yeah, from the red one to the blue one, we're going from 0, 0, 1, 2, 3. So we're shifting left 3. So that makes a little bit of sense. For the last one, we have the number on the outside. And when the number's on the outside, that means we're either going to shift up or down. So we're going to do a vertical shift. So in this case, we're going to shift up 8. And so for these ones do make sense. So plus does mean up for the shifts up and down. So again, if we get rid of this 3, we put the 8 on the outside. So we can't see it because, again, this graph only goes up to 6. But if we scroll, we can see that we go from 0 to 8. Now, you got to be careful because it does look like it shrinks. It doesn't actually shrink. It just kind of moves up, so you can't see as much of the graph. But these are the same size. And the way we can tell that they're the same size is if we look at the slope. Here we're going from 0 to 8. I can go to 2 and 10. So I can go up 2 over 2. And here's same thing. If I go 0 to 2, I'll go up 2 over 2. So it's actually the same size. It just is it's an optical illusion just because you can't see as much up there. But the correct answer is up. So there's no stretches or anything. The only thing that changes the size of it is if the number's on the outside for multiplying. So if we're multiplying outside, that does change the size of it. These ones do not change the size. They just move it left, right, or up, down. All right, for number 2, we need to write the 4th root of x to the 9th using rational exponents. So remember, the little index number is the denominator. The exponent is going to be the numerator. Oops, not numerator, numerator. And then our x that we have, whatever we have in here, that base is going to stay as the base. So our argument's still the base. So we're going to do big X because we have x as the base. And then for our fraction, we've got 4 on the bottom. So we're going to do little 4. And for our numerator, we've got 9. So we've got little 9. That's it. We're already done. So there's not really much else to do. That one's just a translation question. So number 2 is already done. For 3, formula A equals 6v to the 2/3 relates the surface area A in square units of a cube to the volume V in cubic units. What is the volume in cubic inches of a cube with surface area 24 inches squared? So got a little geometry question. So they tell us that the surface area is 24 inches squared. So we're actually just going to plug that in for A. We're going to plug that in for the area. So 24 equals 6v to the 2/3 power. To solve it, we're trying to get v by itself. So I can divide both sides by 6. So I get 4 equals v to the 2/3 power. And so now this is a little bit tricky. So we could always guess and check. So we could just try some numbers to find something that works. But it's a little bit easier if you take the denominator, which is the blue, so I'll stick with blue, and we want to get rid of the denominator. So if I want to undo divide by 3, I would have to multiply by 3. So I can do a 3 on the other side also. So 4 to the third power, so we could type it in, but we're better. So we're going to go 4 times 4 is 16. 16 times 4 is 64. So we got 64 equals v squared. And again, if you want, you could throw this into a calculator to just guess and check. You could use logic to think, okay, what squared is 64? Or if you want, you could think, oh, okay, I can square root both sides to get 8 equals v. So that's our answer. So there we go. So that's what we got for number 3. All right, for number 4, we have to do one of these equations with the fractional exponents. So if we see we've got these two that we're multiplying. So in class we did this. If we're multiplying, what we're going to do is we want to add the two exponents together. So x over 3 plus x over 4 equals 5 to the 21. And now we can see all we have are the two 5s. So the 5s are going to cancel each other out, because if the bases are the same, the exponents have to be the same. So we get x over 3 plus x over 4 equals 21. And now we have to add the fractions up. So to add the fractions up, we need to get them to be a common denominator. So in this case, I'm just going to do 3 times 4 to get 12. That's actually the smallest one, but we can make it work out. You can always make it work out by multiplying those two numbers together. So 3 times 4 would be 12, so that's got to be 4x. 4 times 3 is 12, so that's got to be 3x. If we add these two together, 4x's plus 3x is 7x's. And when we add fractions, the bottom doesn't change. So we get 7x over 12 equals 21. To solve it, we have to get rid of the bottom of the fraction, so we could do that with multiplying. So there we go. And again, we probably could multiply this one out in our heads, because you can do 20 times 12 and then add another 12. But if you want to see it in the calculator, 21 times 12, 252. So we get 252. So we get 7x equals 252. One last step just to get the x by itself, and then we'll be done. We divide both sides by 7. And so then we get x equals, so 252 divided by 7 is probably going to be 36. 252 divided by 7 is 36. So I got x equals 36. How did I know it was 36? I kind of cheated a little bit. I did 21 divided by 7 is 3, and then 3 times 12 is 36. So I broke it up into factors. But you don't have to. You can always use the calculator to check it out. All right, so that's what we got for number 4. For 5, we've got another one we got to solve, but this time the big numbers aren't the same. So this one was pretty tricky in class, but we said we want to try and make the big number into the smaller number. So since we've got a 9, we're going to pick 3 to some power. So 3 to the first power is 3, so that's not what we're going to pick. We need to get to 9. 3 to the second power is 3 times 3, which is 9. So 9 is actually 3 squared. Everything else stays the same. X plus 5 is 3 to the 3x minus 17. Then we have to use our rule that says power to a power means we're going to multiply. So we're going to turn that into 3 to the power of 2 parentheses x plus 5 equals 3 to the 3x minus 17. And now we're in business. So now we can solve it just like the last one. So we can go ahead and cancel our 3's out. So we get 2 parentheses x plus 5 equals 3x minus 17. We can distribute just like we did in Unit 1. So 2x plus 10 equals 3x minus 17. And we're going to get numbers on one side, x's on the other. I'm just going to subtract 2x because it looks like that's going to be easy, because then this gives me 3x's minus 2x's is just x, or 1x. I can now add 17 to both sides. So 10 plus 17 is 27 for x. And then we're all done. That's it. So again, that first part's a little bit tricky, but remember, we're always trying to change the big number into the small number with some power. And if you're not sure, you can always double check with the calculator. So always just check those powers at the calculator. You can even make a little table if you're not sure. Since we know the number that we want to capture is 3, we could just come over here and say, okay, 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. 3 to the fourth is 81. So we could just try all these out in a calculator, and then once we get to the number that we want, we can just say, okay, that's the one that we want to pick. I want to pick 3 to the second power. All right, for 6, determine which ones are exponential. So we want to remember the definition for exponential is that we're going to multiply or divide by the same amount every time. So that's the idea. So remember, our linear ones, we wanted to add or subtract, but for exponentials, we want to multiply or divide by the same amount every time. So if we check the first one, we have to get from 0 to 1, and we actually cannot multiply to get from 0 to 1, so this one's already out. So you just can't do it. You can't multiply to get from 0 to 1. To get from 7 to 7 over 3, we can divide by 3. So first step actually worked. So then for the next one, to get to 7 over 9, we divide by 3 again. To get to 7 over 27, we divide by 3 again. And to get to 7 over 81, we're going to divide by 3 again. So that all works out. So I'm going to pick C. I guess I did them in a backwards order, but that's all right. Now, if you didn't see that, that's okay. There's actually a way to double check them with the calculator. You actually start from the back and work your way the other way. So we've got 7 over 81. This is going to take a little bit of time to plug in, but 7 over 81. And then we have to divide that by 7 over 27. And so we get 0.33333333. Okay, so that's great. That gives us one of the answers. What did I do? Again, I just took the last 2 boxes and I divided them. So I checked out these 2 and I got 0.33333. Now I have to check the next 2. So I start from the right and I go to the left. I go backwards. So 7 over 27 divided by 7 over 9. So 7 over 27 divided by 7 over 9. And we can see I get the same thing. I get 0.33333. If I were to try the next one, because I have to try all of them, so 7 over 9, 7 over 3, same thing, 0.33333. I got to try the last one. 7 over 3 over, it's just 7, 33333. So it does work out. So all of those give me the same answer. So that's how I know C is going to work. All right, now let's try B. So B is down here. So if I start at 5, I have to get from 5 to 10. I can do times 2. It's a really bad times 2. But 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 80. So we can pick B. For D, this looks kind of hard to go from 8 to 8.2 to 8.1. But if I look, it looks like this is a subtraction. It looks like we're subtracting every time. So I'm a little bit suspicious about that one. I don't think that one's going to be it. But just to double check, let's use our trick. Let's do 7.8 up top divided by 7.9. So we get 0.987. And then 7.9 divided by 8 is a different number. So we see we get different numbers. So since those numbers are different, we can tell that it is not exponential. All right, Smart Notebook crashed, but there you go. So we left off, we found that those 2 were different. So all we have to do is just get rid of choice D, because choice D does not work because those are different values. So we're not multiplying or dividing by the same thing every time. That's what I forgot to write on here. Oops, I forgot the definition for exponential. Multiply or divide, that's an of. So remember, exponential is multiply or divide by the same number every time. There we go. All right, so that's what we got for that question. So that's number 6. All right, for number 7, we have to identify all the key features of 6 to the power of x. So we can do that either by just analyzing the equation, or we can do that by making the graph. So if I want to just do it by analyzing the equation, the y-intercept is the same thing as if x were equal to 0. So 6 to the 0 power is 1. So the y-intercept is 1. That's pretty easy. The asymptote for most of our exponentials, because we're not really moving them, is going to be the line y equals 0. So just the x-axis. So that's just going to be our asymptote. The domain for all of the exponentials is all real numbers. So you can either do the all real numbers, or if you want, you could do negative infinity to infinity. The range is always going to be from the asymptote and then up. So our range in this case is going to go from 0 to infinity. We want 0 to have little parentheses. Savasa is making us do y is greater than 0. So if you want y is greater than 0, that would also be a correct answer. So both of those are good. So let's check it out in the graph. So we got 6 to the x. Oops, that's my recording. So let's get rid of these. Let's get rid of all these actually. And we're going to graph 6 to the power of x. All right, so if we go home, so that graph doesn't look super exciting, and it does look like it hit 0. That gray dot's trying to trick us, and even these numbers are tricking us. But if we were to zoom in, that blue line is actually not at 0. You can see it's just getting slightly above. So even though it's at 0, so now we're at 0.006, so it never actually touches 0. So we have to watch out, because it looks like it goes to 0. Desmos tells us 0, but it's not actually 0. 0 is where the asymptote is. There's our y-intercept right there. It's at 0, 1. So we could do 1 or 0, 1. The asymptote is y equals 0. If I type that in, y equals 0, we can see that's the line that the blue one kind of rests on. So that never actually touches that green line. It never goes past that green line. If we want to make it fancy, we can. We can make it a little dashed line. What else? We got the domain. So we can see we're always going to both the left and the right. So that blue line, let's turn the green one off real quick, keeps going to the left, and it will keep going to the right. We could zoom out a lot, and it will, even though it looks like it's going up, it is still going up and to the right. And then for the range, it starts at a little bit above 0, and then it's going to shoot up to infinity. So range, remember, that's bottom to top. So that's what we got for all of those features. So that's it. That's all we have to do for that one, is just name those. Nice thing is for C and D, that's pretty much the same for all the exponentials. Just watch out in case one of them gets flipped. But actually B is also the same for all exponentials, and A is mostly the same. So I would expect these to probably be very similar, if not the same answers. For 8, graph f of x equals 2 to the x and its asymptote. So a couple ways we can choose to do it. If you want, you can make a little table. I think that's going to be kind of easy for this one. I've got x and y. So we can do 0. We can do -1 if we want. 1, 2, 3. Let's just get a couple points on here. 2 to the 0 is 1. 2 to the first is 2. 2 to the second power is 2 times 2 is 4. 2 to the third power, 4 times 2 is 8. We could even do another one. 4 times 2 is 16. We could even do another one. 5 times 2 is 32. We could even go backwards. 1 divided by 2 is a half. We could even go backwards. Half divided by 2 is 0.25. And we can plot these points. So 0.2, 1, 1/2 is pretty low. 0, 1 is pretty low. 1, 2 is pretty low. But then 2, 4 gets a little bit bigger. 3, 8 gets a lot bigger. 4, 16 gets a lot bigger. And then 5, 32 gets really big. So we can see, again, that's got that good exponential swoop that's going on right there. So if we graph it, we just want to connect those with a nice little swooping curve. So we're going to do a little swooping curve as best I can. We're going to want this to keep going all the way out, being very careful to not get past the asymptote, because it says to also graph the asymptote. And so remember, the asymptote is always this line. Well, not always, but almost always for what we're doing, this line, y equals 0. So y equals 0 is nearly always the asymptote. So that's what we get for our nice little graph there. And again, we can graph it in Desmos. Instead of 6 to the x, we want 2 to the x. Let's go back home and make it look a little bit nicer. We can see we get that same swooping curve. And if you want to get those dots, again, you can go over here to the settings and just turn it into a table. And now look, it's got those same dots that I put it in those tables, and even plots the dots on the graph. So you do want to be somewhat accurate with this. Again, accuracy is important. If it looks like a straight line, or if it looks like you're just connecting them with straight lines, that doesn't count. You have to actually graph it with the little swooping curve. And you have to be careful not to jump above the asymptote, jump below the asymptote. You want to be right on top, resting on top of the asymptote. So you have to be careful to graph it accurately. All right, for number 9, what's the rule that defines the function represented by the table? So for this, we just have to use our equations. This is pretty quick. It's going to be y equals a times b to the x, where a is always the y-intercept, or the starting amount, and b is what you multiply by. So it's important that it's always what you multiply by, because if it's division, you're just multiplying by a fraction. So if you divide, you're really multiplying by a fraction. X always stays as x. So if we look to see what we've got, the y-intercept, what we're starting at, is 60. So y equals 60. B is in parentheses. That's what we're multiplying by. And so again, if I go from 60, I'm dividing by 3 to get to 20. So divide by 3, we write as 1/3. Because we're going to do divide by 3, we have to write it as a fraction. X is x, and we're done. That's it. So that's all we got to do. Done with number 9. So we just have to know that equation and know that's what the A and the B stand for. All right, so for 10, a wildlife biologist determines that there are approximately 250 reindeer in a region of a national park. The population decreases at a rate of 15% per year. What is an exponential function that models the expected population? Believe it or not, we're just using the same equation. Y equals a times b to the x. Oops. So y equals a times b to the x. All right, well, a we said was the start, so that's 250. So far, so good. B, for B, it says we're going to decrease by 15% each year. So that means we're going to have all 100% minus 15% every year. And we're done. That's it. That's all we got. So all we got to do is realize that a decrease is going to be a minus sign, 0.15 for 15%, and that's it. That's all we got to do for 10. That's another quick one. For 11, business purchases a 3D printer for $6,000. The value of the system decreases at a rate of 10% per year. Write an exponential function to model the situation. Y equals a times b to the x. That's kind of the star of the show for this section, so we're going to use that equation quite a few times. The start, 6,000. So 6,000 is the start, so we're going to put that in for A. For B, B is what we're multiplying by every time. In this case, we're going to decrease by 10%. So 100% minus 10% to the x, and that's it. Our equation's done. So we did part A. Part B says determine how much the printer will be worth after 5 years. So to do that, we're going to take the 5, plop the 5 in for x. So y equals 6,000. You could simplify this down to 0.9 if you want, but I'm just going to leave it as is for right now. To the 5th. And now this is definitely one that you got to throw into the calculator. So there's really no other way to do it at this point than to throw it in the calculator unless you want to do a lot of calculation by hand. We don't need our table anymore. But we've got 6,000 parentheses 1 minus 0.10 to the 5th power. And we get 34, 35, 42, 94. So 35, 42, 94. $35, 42, 94. That's it. We're all done. So we're all set with that one. So it's a really quick one. We just plugged the 5 in. So there we go. All right, we're moving on to 12. So for 12, compare the two bank options below. So we have Sun Bank and Moon Bank. So for each of the banks, the principal is the same. So we don't really care about that. The annual interest is the same. So we don't really care about that. The number of years is the same. So we don't really care about that. But what's different is that we have one of them is compounded daily and the other is compounded monthly. So this is really what question A is asking, is to compare daily versus monthly. Which one you make more money with. Oops, this should be a 5, not 10. Oops, that's a 5. So we just ask ourselves, all right, do I make more money if I get paid every day or every month? So again, even though we're getting paid a smaller amount every day, that extra interest on what you're paid adds up. So we already know that the answer has to be Sunbank because a daily rate is going to pay more than a monthly rate. Same thing, a daily rate will pay more than a quarterly rate. A daily rate will pay more than a yearly rate. So the number of times this n value is going to be bigger than this n value. So the daily is going to be bigger than the monthly. So we don't have to do any calculations there. This is a comparison. So remember, our idea here is larger n, more money. All right, so then it says, how much will the value be after 5 years for the bank you chose in Part A? So what we have to do is, this is going to be tricky because we have to set up now the situation for Part A. So I'm only looking at Sun Bank because that's the one that I picked. So I don't have to use any of the numbers for Moon Bank. Don't use any of that. So what we're going to do is use our equation. Y equals A times B to the x power. So this is the one that's a little bit tricky because the interest rate equation is a little bit long, but we have our starting amount. Starting amount is 12,000. Our rates, we're going to get money. So we're getting an annual interest. We're going to get money. So it's going to be a 1 plus 0.04 because that's our percent. And then we've got our number of compounds. So we have this daily here. So for the daily, since it's daily, we have 365 days in a year. And up in the little exponent, we have to do 365 times the number of years. So we've got 5 years, so 365 times 5. So that's all of our parts. Now again, I went off of the y equals a times b to the x equation. If you want to go off of the interest rate equation, that's going to be the amount is equal to the principal, 1 plus the rate over the number of divisions to the number of divisions times the time in years. So you can go off of the big equation if you have that big equation down. If you don't have the big equation down, you have to kind of think about it and build it from the small equation. So it might be worth it to remember the big one. Also, this is one that you can use in your daily, not daily life, but in real life when you're looking at your own investments when you get a job, or if you're going to go into debt to get maybe like a car loan to buy a car. This is the equation that tells you how much you'll have to actually pay for that car. So might be useful to know. Either way, we're just going to throw this into a calculator from here. So 12,000. 1 plus 0.04 over 365 to the power of, and we definitely want to have the parentheses here, otherwise Desmos is going to throw a fit. So we got to make sure we get those parentheses. 365 times 5, and so we get 14,656. And then our change, 0.67. So again, 2 decimals make sense because it's money, so you probably want to go dollars and cents. So in this case, we made over $2,000 by doing nothing. We just put the money in the bank and just let the bank give us some interest, and we made $2,600. Not too bad. All right. For 13, there are approximately 5,000 frogs in the lake. The population grows at a rate of 7% per year. From year 1 to year 4, find the average rate of change of the population in frogs per year. So what we want to do is set up our equation y equals a times b to the x. So again, if we look to see our initial amount A is we've got 5,000 frogs. B is our rate, so we're going to grow at a rate of 7% per year. So this time we get to do 1 plus 0.07, and then years is just going to be the x. So that's our equation. So we need to go from year 1 to year 4. Now, this is where you got a lot of different options you can take. One option I'm going to take in Part A is going to be maybe the long option, but it's kind of nice. Since we want to go from year 1 to year 4 to find the average rate of change, which is the slope, we can just use the slope formula. So the slope formula is y2 minus y1 over x2 minus x1. So in this case, we're going from 1 to 4. This is not a very good 2. So what we're going to do is plug in our y2. So we would plug in our value at 4. So 5,000, 1 plus 0.07 to the fourth, minus however much we were at 1. So 5,000, 1 plus 0.07 to the first power over 4 minus 1. So this is what our calculation is going to have to become. Now, I'm not going to throw this all in at once, just in case I make a little bit of a mistake. It's nice to do kind of each part separately, just to double check to make sure things are reasonable. So always good to do that reasonability check. 5,000, 1 plus 0.07 to the fourth power is 6,554 frogs. Okay, that makes sense because we're gaining frogs. We probably don't want to be too much more than 5,000, so that makes a lot of sense. So 6,554. I'm rounding up to the nearest frog. It doesn't make sense to carry decimal frogs. Either you have a frog or you don't, so I'm going to stick with a non-decimal. If I put the 1 in there, I get 5,350 frogs. So minus 5,350 frogs. Again, that makes sense because it's a little bit more than 5,000. 4 minus 1 is 3, so that's good. So I got to do 6,554 minus, I see on the screen, I got 5,350. So I got 1,204 frogs. So I gained 1,204 frogs over 3 years. So to get the average rate of change, I have to divide that by 3. That's not going to come out nice. So close. 1,204 divided by 3, 401.3 frogs. And again, if we're counting frogs, to the nearest frog is totally fine. It's about 401 frogs. Again, about 400 frogs would also be okay. Again, it says approximately 5,000 frogs in a lake, so it's possible that you missed one of the frogs out of the 5,000. That's totally fine. So that's one way to do it. That way makes a lot of sense. We're just finding our ending value at 4 years, subtracting what we're starting with at 1 year, and then finding out what the change was. If we want to be a little bit fancier, since we did get the equation, we could actually just type the equation in. 5,000 parentheses 1 plus 0.07 to the x. Now, I could find this graph. It's kind of far away because we can see we're already up at 5,000. So I'm going to have to change to get all the way to 5,000 in the y's. So we got to get up to, let's just put 10,000 in. So the graph doesn't help out too much because it's not really granular. It's tough to kind of see what's going on at all of these years. But what is helpful is making the table. Oops. So right there, we can make the table. And now if I make the table with these dots down here, I can just say the years I want. So look, I already have year 1. If I typed in year 4, it would give me the answer for year 4. And it does bring the dot up too, so I don't have to go and select it over there. So I'm going to do that for the second part. Now I still have to use the average rate of change formula. The average rate of change formula is the slope formula. So it's still y2 minus y1 over x2 minus x1. So I got to find out what I'm at year 8. We know that's going to be 8 over 5, so that's going to be easy. But at year 8, it's 8590, or 8591 if we round up. For 5 years, I can just change that to a 5, or if I want, I can just make a new line, put a 5 in there. 7113. Sorry, 7013. All right, so I got my number of frogs, I got my years, so we got 3 years, and we got to find out how many frogs. I gotta get out of the table now. And I can still see the numbers up there, so I can easily subtract 8591 minus 7013. So I get 1578 frogs. Now 1578 divided by 3, that is going to come out nice. So good. So we got 5. That's going to be 2, 6. But we'll throw it in. 1578 divided by 3 is 526. Kind of cool. How did I know that was going to come out nice? I just add these up. 1 plus 5 is 6, plus 7 is 13, plus 8 is 21. 21 divided by 3 works, so it'll come out nice. All right, using your answers from part A and part B, the rate of change increased by about how many frogs per year? So what we're going to do is say, well, the rate of change increased from, well, I should say decreased, no, increased. Went from 401 to 526. So 526 minus 401 should be 125, but we'll throw it in. 526 minus 401. So we get 125 frogs per year. So there we go. So again, up here from years 1 to year 4, we get 401 frogs per year. In year 5 to year 8, we're getting an extra 526 frogs per year. So in the second section, we're getting an extra 125 frogs per year compared to part A. So there we go. So it is a little bit long, but it is also like a review because it's really just the slope formula. So we're just using the slope formula with our equation. So it's kind of cool that we can put everything together for one big question. And the question, even though it was a little bit long, it wasn't like it was super complicated. There wasn't a ton of formulas to do. There wasn't a ton of algebra to do. It's just a little bit of plugging into the slope formula and understanding how to build the y equals a times b to the x equation. All right. Well, I know most people are probably almost done after this since that one is a long one, but there is one last question. So we just got a little graphing question. So it says graph and label the following two functions. So we have to do f, which has an initial value of 100 and is increasing at a rate of 10%. So if we know it starts at 100, we can label f and say f starts there. If it goes up by 10%, we've got 100, 1 plus 0.10 to the x power is the equation. And just like before, if we want, we can just go ahead and make the table. Let me turn this one off just so we can see what the other one looks like. So 100, 1 plus 0.10 to the x power. And again, we get the little settings and we can make the table. And so there we go. So we care 100, 110, 121. So if I want, I can start plotting those points. So 100, 110, 121. I probably want a few more points. That doesn't look like enough points. I don't really want the negative ones because it tells us it starts at 0. So we got 133, 146. So 133, 146, 177, 194. So 177, 194. Oops. So 214, 235, 214, 235, and then it's, oh, I got off kilter somewhere. Oh, I think that looks good because it does look a little bit janky there. That doesn't look like it's got a good curve. 161 is 5. Yeah, there we go. All right. 161, about there. All right, and we can see we're kind of making a curve. So we don't want to do a straight line. We want to do a bit of a curve. For the other one, has an initial value of 80. So we're going to start here at 80. And we're going to decrease at a rate of 5%. So 80, 1 minus 0.05 to the x. And so we can throw that in. And to save myself some time, I think we can do this. Let's see if it works. Nope. Minus 0.05 to the x. So we don't want that table anymore. But we want to make a new table. So we do settings and then table. All right. I'll even go home because that might show up. Nope. So there we go. 3, 4, 6. So there we go. So 80 and then 76, 72, 80, 76, 72, 68, 65, 68, 65. So this one's a little bit nice. And then 61, 58. All right, we can kind of see. All right, yeah, we're going like this. That's not very good. Oops, I don't like that one. That didn't draw well. Let's just see what it looks like. There we go. So, yeah, Yeah, so these dots are kind of close on my screen, but we can kind of see it's going to go like this. It's kind of far because 9 is 50. That's a tough one to graph. Let's put the 50 in. And then let's make the swoop look like that. Whoa, man. This is a hard one to draw. Let's go this way. Maybe this will be better. That looks a little bit nicer. All right, so that's what we got. We've got our two curves. That's it. That's all we got. Oh, we didn't. We got to label this one G. We almost messed up. So the bottom one is G, the top one's F. So F is the one that's increasing, G is the one that's decreasing. So that's it. That's how we do it. So anyway, that's the entirety of the quiz. I do want to bring up, where is the calculator at? We're gonna bring up the calculator. The reason I want to bring up the calculator, so if you got the TI calculator, I just want to show you how to put these ones in, just to close everything up. So remember, if we're doing our absolute values, so let's go all the way back up to the absolute values. If I wanted to do absolute value of x and then absolute value x plus 3, we go y equals, and we have to go to math, over to number, and we're going to pick ABS for absolute value. So there's absolute value of x. We can do math over absolute value, and we can throw in x plus 3. And so that we can see we got the same graphs that we saw earlier in Desmos. So that's how we do the absolute value. Let's see, what else did we throw into Desmos? Well, I mean, we threw that, that's just dividing, so we know how to divide. 6 to the x power. So if we want to put in the 6 to the x power, because we looked at that graph, we can do 6 to the power of x, then hit the little graph button, and we'll see the 6 to the x power. So we can see that exponential curve that we saw. If I want to get the table, I can just hit second, and then up here in little blue, it says table. And I do get the table. So I can bring up the table like we saw in Desmos 2. So if you like the table, you still get the table in the TI calculator. It'll still give you the table. What else we got? So we did the table. We did that. We didn't use the calculator much for those ones. Didn't really use the calculator except to plug this in. Just to repeat this calculation in the TI calculator so we know what buttons to press. It would be 12,000, parentheses, 1 plus. To do the fraction, you can do alpha y equals and make the little fraction. 0.04 over 365 to the power of, and you can see the TI is not as picky as Desmos, but I'll still put in the parentheses. 365 times 5. So we can see we get the same answer as we did with the other one. So 14656, 67. So there we go. We get the same answer with that one. So that's how we do 12. With 13, again, I already showed you how you can bring up the table if you want to bring up the table. So the table will work out. It's actually kind of nice in the TI calculator if we plug this in, 5,000, 1 plus 0.07 to the x. I actually think the TI calculator is nicer for this one. 1 plus 0.07 to the x. And the reason is, since we're only dealing with numbers from 1 to 10, I can just hit trace, type 1, and press enter, and I can instantly just get the value for 1. I can press 4 and press enter, and I can just get the value for 4. So it's like it plugs it in for you automatically. Again, we can do 5, and we can do 8. So, I mean, it'll just give you all of these answers really quickly. Obviously, if you want to go to the table and just grab the numbers from the table, you have that option too. But the TI does have that nice trace feature that just solves everything if you want to plug in a number. And it just gives you the number right away. So that's really cool with the TI calculator. And then with this one, again, kind of the same deal. If we want, we can graph it. And again, you can hit the trace button or you can use the table. So that's a little quick summary of all the TI commands as well.